Section 3. Further applications of related rates. An advanced warning before starting this section. The first 1/3 of this section, namely 3 and 3.2, those are for everybody. Now, how about the rest? Well, those are rather intrinsic to the applications to business calculus and financial calculus and econometrics, calculus-based econometrics. In short, if you're into the application of calculus that are modeled and measured and represented in terms of monetary units, such as dollars and other currencies, things like those, if you like those, then yes, you have to study these. If you're not into any of those, say for example, if you're not going to business, finance, or economics, and you're majoring in, say, life science or health science, in that case, you may want to skip these. But still, the first 1/3 is for everybody. So let's begin. Suppose that we have a certain quantity y that changes with time so that it can be represented as a function of time t. In this case, y of t. Then, the relative rate of change of y is defined as y prime over y. That is, the rate of change with respect to time over the current status. Now, frequently, the relative rate of change is expressed in terms of percentage, the percentage of the current status. In that case, we call it the percentage rate of change. Now, this may be a bit too advanced, but let me talk about another aspect of relative rate of change. And this is particularly important for life science students, biology or health science. The logarithmic rate of change and the relative rate of change, these two end up being the same thing. That's because of this computation. Take the derivative of log of y, and by the chain rule, we take the derivative of the outer function, that's log of y, so we have 1 of y, times the derivative of the inner function, dy dt. That's by the chain rule. So in the end, what do we have? We have y prime over y. That's the very same quantity as the relative rate of change. So the relative rate of change and the logarithmic rate of change turn out to be the same. And consequently, many of those relative rate of change have logarithmic units. Okay, let's stop there. I don't want to get too advanced here. Okay, so much for the theory of relative rate of change, and now let's go to an example problem. This example comes from biology. Here we go. Basset's law expresses the blood flow F as a function of the radius of the blood vessel as follows. Right here. F is kr to the 4th power. That is, the blood flow is proportional to the 4th power of the radius of the blood vessel. Here, k is just a proportional constant, so it doesn't change. It stays the same. So this is a relationship between F and R. Now let's go to the problem here. If the radius of the blood vessel increases by 12%, by how much percentage will the blood flow increase? So the blue part, the condition part, is the part we know, and the red part is the conclusion that we want to find out. We don't know yet, but we have to find out. Now, just by reading this, can you still see that this is talking about the percentage rate of change? Maybe you can see it because of this 12%. Well, let's imagine this. Suppose that I change this problem like this. Blood vessel increases by, say, 1/3. By how much will the blood flow increase? How's that? Can you still see this is talking about the relative rate of change? It's trickier. We don't have this 12% coming out explicitly, suggesting the percentage rate of change. Can you still see this is a relative rate of change? It's tricky. So let's analyze this a little bit further. If the radius of the blood vessel increases by 1/3, 1/3 of what? 1/3 of certain unit? 1/3 of the current radius. That's hidden. So 1/3 of r, that's hidden. And then in the conclusion part, how much? How much of what? Well, that part is a little clearer because you already took care of this. So how much of or how much in comparison to or relative to, yeah, that's even more straightforward. Let's go back to the original problem. 12% of what? 12% of the current radius. And how much percentage of what? Those are hidden. Now it's very, very clear that we are talking about the relative rate of change. Okay. So what does this blue part say? The radius increases. Okay, we are talking about an increase. So this is rate of change. The rate of change is 12% of the current radius. So r prime, the rate of change, is 12% times the current radius. Do you see that? Therefore, r prime over r is 0.12. That comes from this blue. If you prefer the German notation, then you can re-express it as dr dt, and then this one is r like this. You can write like this. But me, I prefer prime notations. It's simpler, and also this notebook is written in Wolfram Mathematica, and it does programming as well. And in symbolic computation, you need some programming, and that Mathematica language is based upon French notation with primes, and the DRDT thingy is not really supported unless you do something fancy with this window. Okay, that's the blue part. Now let's go to the red part. What do you want to find out? We want to find out the amount of increase. So f prime is the question, but then again, what percent of the current blood flow? So basically it's this situation, and we want to find out this percentage. In short, this is f prime over f is something, and that's something we have to find out. Make sense? And then of course, in case if you prefer this Leibniz notation by like this, and you can rewrite like this too, in case you prefer. Our textbook author prefers the German notation. Me, I prefer French notation, so let's stick to those. Okay, all right, we analyzed the problem here. Now let's answer this problem completely. This is something we can hold on to, the relationship between f and r, but then again, that's not complete. This is a relation between only the original functions. How about the relation between the rates? The relation between f prime and r prime? Well, you can find out through the implicit differentiation. Let's take the derivative, f prime, and take the derivative implicitly. So 4 comes out as coefficient in r to the third power, but that's not it. We need r prime. Remember, this is implicit differentiation. we are talking about the related rates. So primes pop out every single time. Now, if you somehow prefer German notation, then you may want to do it this way. And then write it as like this, if you prefer it that way. All right, this is what we have so far. Now, what do you want to find out? We know r prime over r, and we want to find out f prime over f. What is f prime? It's right here, the numerator. And what is f? It's right there. That's the denominator. So we want f prime over f, and that is 4k r to the third power times r prime, yeah, that's the numerator, and divided by kr to the fourth power. Make sense? Let's make a little bit bigger so that you can read better. F prime over f, numerator, denominator. And then some simplification is in order. You can immediately clear out those k, and then r to the third power, and then fourth power. So we have 4 times r prime over r. That's my conclusion. So f prime over f, something we want to find out, is 4 times the r prime over r, which we know the problem gave you as 12%. Now, if the problem is like this down here, you'll have to put in 1/3 over there. I don't want to confuse you, so let's go back to the original problem. So that's 12%. So 4 times of 12%, the desired answer must be 48%. So the answer is 48%. Is that clear to everybody? Okay, what did I do in my answer key here? Yep, the very same computation. Original and the implicit differentiation. And then we want to find out the relative rate of change, f prime over f. So divide one from the other. And then after simplification, we get 4 times r prime over r. And here's the conclusion. The relative rate of change of f is 4 times the relative rate of change of r. So multiplying by 4 to 12%, we get 48% increase. Solution 2 is exactly the same too, except that I use German notation. All right, so much for relative rate of change, and that much is required to everybody. For the rest, as I told you before, the rest, the other 2/3 of section 3 is for the students who are going over to business calculus or financial calculus or calculus-based economics. In those cases, the latter 2/3 will be important. Otherwise, you may want to skip.